Welcome guys in this new video tutorial series of quantum computing using Python. In this tutorial series we are going to learn about the fundamentals of quantum computing using Python code. Let me open my Colab notebook where we are going to learn using coding. The first thing we need to install is a library called Qiskit, and I'll be installing Qiskit along with some dependencies. So I'll be using Qiskit all. So after writing Qiskit, you have to write all in square bracket. So Qiskit is nothing but Quantum Information Science Kit, and it is open source framework developed by IBM for programming quantum computers using Python. And when I write all, so basically I'm installing Qiskit core packages plus some optional extra packages. It is not mandatory, but it is a good practice to install those things. So this is how Qiskit will be installed. Now Qiskit is a very important library. It is a fundamental library and you need it to write your Python codes. Okay, now there is another library that is again equally important. Sometimes it is installed with Qiskit all, but many times it has to be installed individually. That is Qiskit-AER. Now this is actually Qiskit Advanced Emulator of Reality, and it is basically a high performance simulator for quantum circuits. So instead of needing a real quantum computer, you can use AER to simulate quantum behavior locally on your classic machine. Now let's check the Qiskit version. This is not mandatory, but it is good. Let's see what version, what number of version currently we have with Qiskit. So let me write a display message, that is Qiskit version. Okay, and then the command is Qiskit dot double underscore. Remember, it is double underscore version, and then again it is double underscore. So let's run this. Okay, the current version is 2.0.0. Okay, now let's start with our first code of today, and writing this code will be understanding the fundamentals of quantum computing as well. So what we are going to do today, we are going to create a qubit 0. So the first thing, what is a qubit? So in classical computing we call bit. Bit is nothing but 0 or 1. Here it is qubit in quantum computing. Qubit is short for quantum bit and it is fundamental unit of quantum information. Similar to a bit in classical computing, but with quantum properties. So qubit can exist in 0 state, 1 state, or it can be a linear combination. It means that it can be a blend of both 0 and 1 simultaneously. So we need to install certain libraries, and meanwhile I'm typing those libraries, I'm telling you about that qubit thing as well. So you can see here I have written create, then 0 with in between pipe and greater than sign. This is a special symbol and it is known as bracket notation developed by Paul Dirac. So this notation is used to represent the quantum states and inner products. So basically what you can say that this is the basis vector of 2D complex vector space that a qubit lives in, and the symbol pipe and this greater than in 0, it comes from Dirac's bracket notation. So it is a vector representing a quantum state and it is used to describe and manipulate the quantum systems mathematically and conceptually. I'm not going in mathematical part currently, so leave it here only. Okay, so meanwhile these are certain libraries that we are going to need. Visualization is not important, but currently I'll not show you in this part what this visualization will do, but let's write it here. So these are some fundamental libraries that we are going to use. Okay, now all these libraries are done. Let's start with our code. So first thing what we are going to do, I'll also print the compilation time here. So let's start with start time. For that we had this time module. Okay, the first thing that we are going to need is we have to create a quantum circuit. So the function is quantum circuit, and here I'm going to write two values, that is 1 comma 1. The first one is qubit of 1 bit, and second one is classical bit of 1 bit. Now why I need this thing? Because you cannot measure a qubit when it is in running state. The second thing I need is to measure. So what I need to measure is in which position? 0th position, and I have to store it in 0th position of classical bit as well. The first 0 represents index position in quantum state, and 0th position in classical state is the second 0. Okay, so this QC dot draw will draw the quantum circuit for us. Now the next thing is that we need to simulate our code. For that we are going to use that AER simulator, so it will actually simulate our code. Okay, then now I need to compile my circuit. After this I need to compile my circuit, so I'll be using a variable called compiled underscore circuit. Obviously you can name it anything. And quantum computing provide us with a function with a library called transpile. So basically transpile is target simulator. It translate, and it is basically a compiler for quantum circuit, and it is saying that what I need to compile the circuit, that is QC, and I have to put it in that simulator. So this will give me a compiled circuit, and then I need to run this compiled circuit. So I am taking one variable called job, and I'll be running our compiled circuit, and you can run it for n number of times. I am running it for 1000 times. So now basically what this code is going to do, this is going to create a 0 qubit. I am not writing value 0 anywhere, because remember, by default initial value of a quantum value is 0. So you don't need to explicitly mention 0, but if you need to write 1 as your initial value, then you have to explicitly mention it, or you have to use other methods that we are going to learn in coming lectures, that is using gates. Okay, so now I have stored my result, and now I am going to count. So what basically we are going to do here, I have a value 0, and I am going to iterate it 1000 times, and every time I'll get the output 0. This is basic classical computing, but using quantum logics we are going to learn it here. In the coming sections, in the coming tutorials, we are going to learn how to change the state, how to change the phase, and there you can see the actual quantum logics. Okay, so the count will give me a dictionary. The key will be the value 0 or 1, and the value of the dictionary part will be how many times I am getting that 0 or 1. So here we are going to get only 0, and we are going to get it 1000 times. Okay, so I have written all those things here, and now we can run it and see. Okay, you can see here the output is 0, and we are getting it 1000 times every time, and this is quantum circuit. So what we have done here, we have created a quantum circuit. We are giving input 0, and we are getting output 0 1000 times. So this is basic classical computing case, but we have done it using quantum logics. And let me do one more thing. Let me check the compilation time here also. So we have to end our time that we started. So this is the basic fundamental concept of quantum computing. 2 or 3 things that you need to remember. Initial value of a quantum is always 0 unless explicitly mentioned. Okay. Second, we have written quantum circuit. There we have 1 comma 1, that is 2 values. First one is quantum value, qubit. Second one is classical value, bit. Why we need classical value? Suppose you are tossing a coin, you cannot measure the value of coin in mid-air. it has to be in a stable condition. And when quantum value comes in a stable condition, it has to be stored in some classical bit. And that term is technically called collapse. Okay, that collapse, quantum value collapsed and become a definite or stable value. Okay, then measure. So with measure we have 0 comma 0. 0, first 0 is the index position value in quantum state. Second 0 is the index position value in classical state. Okay, so I have written here the end statement. Let me check. Okay, I need F here, the string formatter it is, and let's run this. Okay, so you can see here the time. Let me just make a space here so it will look nicely formatted. Okay, so this is all about the first code that we learned. We have created a qubit 0 and we learned the basic fundamentals of quantum computing. I'll be not going into much mathematical part. This is our first code. Practice it and you will be just understanding the basic concepts. In the later lectures we are going to deep dive and learn the basic concepts more. So that's it for this lecture. Thank you and we'll meet in the next lecture.